And today, the big theme today, and what we're basically going to be working on for the next several days are series. And I mentioned yesterday the relationship between series and sequences. They go hand in hand. You can't have a series without a sequence. So if my sequence is defined by an could be, an could be n squared, it could be 1 over n, it could be whatever you want it to be, then this is a list of terms, a1, a2, a3, a4, and so on, that goes forever. The series is defined to be the summation from n equal 1 to infinity of an. Oh my goosh. That means a1 plus a2 plus a3 forever and ever and ever. It never ends. So a lot of textbooks, and you'll even hear people say, we're going to be working with series. Now today we're going to be working with infinite series. That's kind of a lame statement. The word series means it's an infinite sum. So there's no such thing as a series that's finite. Series are always infinite because there's an infinite number of terms. A sequence is always infinite. You can say, what's the sum of the first 100 terms? You can say, list the first 100 terms of your sequence. That's okay. But when you say series, that means that it adds forever. That, again, is kind of like saying a round circle or a straight line. You don't really need to put the qualifier in there. A series, by definition, is an infinite sum where I have a specific term. Now, our goal over the next week or so is, whenever I'm working with a series, is to figure out when the series converges or diverges. Ooh, so this is huge. So we need to establish and develop a few rules that are governing series. So let's start with something really simple. I want to start with just a few simple terms. Now, we generally give this the name S. S for sum. That's all that means. S for sum. If I wanted only to do, let's say, the first 100 terms, let's just say hypothetically, you wanted to do n equals 1 to 100 of the ANs, then we would call this S with a subscript of 100. And this would be called the 100th partial sum. And it is often the case that we are only interested in a certain amount of terms. There's nothing wrong with this statement. We generally always use an S for the whole series and an S with a subscript if I only want a certain number of terms. That's just notation out of convenience, okay? Don't read anything more into it than that, because we will use terms like this all the time. Now, there's a couple of very simple rules governing series that I would hope that you saw in a Calc 1 class, and that's specifically when I'm adding series together or I'm multiplying series by a scalar. So let's consider something really simple. Let's suppose that I have the sum, and we'll keep it really simple. Let's say I want to go from I equal 1 to n. Now here I'm going to use I as my index because I'm going to use n at the other end. You can use any letters of the alphabet you want, just be consistent. Of AI, that means this is A1 plus A2 plus all the way to AN would be the last number. Now consider another series defined, I'll call it BI. And this is a subscript. I'm not multiplying by I, right? It's down here. So this would be B1 plus B2 plus all the way up to Bn. What I want to know is, what sort of algebra can we perform on a series or sums of series? Well, I would like, first of all, to add these two together. Now, the reason I'm doing finite numbers is so I can actually have a finite number of terms to illustrate, because whatever I determine here, I'll be able to show for infinite as well. So if I said, let's add these two together, we would see that this is A1 plus A2 plus all the way up to AN plus B1 plus B2 plus all the way up to Bn. Now, using commutativity and associativity of addition, we know when we add things, we can add them in any order. And associativity means we can regroup them in any order. So we could rewrite this if we wanted to as A1 plus B1 plus A2 plus B2 plus plus, and then the last one, an plus bn. Okay, clearly I can do that because the a's and b's are just numbers. But if you look at this, isn't this the sum of ai plus bi? Right, a1, a2, a3. So we have just proved that the sum of the summations is the summation of the sum. That's kind of cool. Isn't that a limit property? The sum of the limits is the limit of the sum, and the derivatives, sum of the derivatives is the derivative of the sum. Integrals, the sum of the integrals is the integral of the sum. Those are properties that apply to limits, derivatives, and integrals. They also apply to series. Now, the other property that applies to all of those is the scalar multiple. We know, right? The limit of a constant times a function is the constant times the limit. The derivative of a constant times a function is the constant times the derivative, and so on. I wonder if it's true for series as well. So what if I want to do k times the sum from I equal 1 to n of ai? Well, then that would be k times a1 plus a2 all the way up to an. But if I distribute the k, that'd be ka1 plus ka2 all the way to kan. But you know, that sure looks to me like I'm just taking the sum from I equal 1 to n of k times ai. So a constant times the summation is a summation of the constant times the function. Same as in limits, derivatives, and integrals. These are the only two properties that translate across the board in all those other areas, but they're really, really important. That means when you're working with sums, if it's convenient, you can break up sums. I have a big thing, I can do them one at a time if that made my life easier. It's not always a good idea, but I can do that. So I've got that. Now, we're going to talk about one of the most basic rules. Okay, one of the most basic rules of convergence. So if I ask the question, all right, let's suppose for the sequence defined by an, okay, let's suppose that the limit of as n goes to infinity of an is some constant, let's just call it L for limit. All right. So let's just start with that statement. Let's suppose that I have a sequence and it converges to some number. Keep it really simple. That's not really all that complicated. I could have a sequence, for example, my sequence is, let's say 3n squared minus n over 4n squared plus 5. So if I ask you for the limit as n goes to infinity of an, can we say that the limit is just 3/4, everyone? Would that be an easy one?
Yeah.
Yeah. Okay. I want to keep it simple. I have a sequence. I can easily find the limit. Let's just suppose the limit is L. By the way, it doesn't matter if it's positive or negative. It's just some finite number L. Now, here's the question I have. Now I want to do n equal 1 to infinity of an. If my terms are converging to L, that's kind of like saying I'm going to add up the number L over and over and over and over and over again, forever and ever and ever. In other words, I'm adding up numbers that are getting closer to L, but I'm doing it forever. What would that add up to?
I guess just L.
Yeah.
I'm going to add up L infinitely many times.
Oh, just infinity then.
I think that would be infinity, wouldn't it? Let's just say my limit was 1. And that's basically like I'm saying 1 plus 1 plus 1 plus 1 forever and ever and ever. In other words, this is infinite. Now, if L were negative, then it would be negative infinite. But either way, my series would not be finite. Oh, so if I have a sequence that converges to a nice happy number, that means I'm going to have an infinite sum. Now, convergence for the series is the same conclusion in that if the series is finite, we say it converges to that number. If the series is infinite, we say it diverges to infinity. And if the series can't be found, it diverges without limit, just like the sequence. But I can have a sequence converge, but have the series diverge. It is much harder to get convergence for a series. So right off the bat, if I have my sequence and it doesn't go to 0, my series is always going to be divergent. So this is the first of the very major rules. Okay. Some people call this the test for divergence. And I don't mind that, but that's too vague. So I give it a different name because it's a different name in most books. Because every test we do will technically be a test for divergence. This one's more appropriately called the nth term test. That's the term the expression we're going to use, and that's what most textbooks call this, the nth term test. So I'm going to give you two things. The limit as n goes to infinity of an is equal to 0. And then the last example, it wasn't, it was equal to L. And the absolute value of an plus 1 is less than or equal to the absolute value of an for all. That means for every n after a certain point. And I'll explain what that means. That looks so abstract. I have terms in a series, and at some point, maybe it's on the first term, maybe it's the 27th term, maybe it's the 10,000th term. At some point, they're getting smaller forevermore. And I put an absolute value because numbers can be negative. That's not the problem. It's the size of the numbers. So this says that symbol means for all n after a certain point. My terms are getting smaller. So these two conditions have to be met.
And the capital N means? What's the capital N mean?
I said that's a number at some point.
Just some number.
Yeah, but and by the way, that number can be 1. It can be 1,000. It just means at some point. Now you go, why is that important at some point? Because remember, it's going forever. Oh, it might take a while, but now my numbers are getting smaller. Here's what happens sometimes. My numbers get bigger at first, and then they get smaller down the road. That happens. At some point, if my numbers get smaller forevermore, then I say they get smaller, period. At some point, that's all I care about. More often than not, it happens right away. Now, these two conditions, if they are met, that doesn't mean I converge. No, it's just the opposite. If either one of these conditions fail, then I diverge. Now, this makes it really simple. If my limit isn't 0, it's sort of like adding that number up infinitely many times. I'm going to diverge. If my numbers aren't getting smaller, if my numbers are actually getting bigger, then obviously it's going to diverge. If this one fails, then this one will fail always. So the second one is less important because they kind of go hand in hand. They're both going to always be true, or they're both going to always be false. Now, this is what is called a necessary condition. I'm going to explain. This is a logic term. And this is very important that we understand this. A necessary condition does not guarantee a conclusion. The failure of a necessary condition guarantees the conclusion won't happen. So here's a simple example I like to use. A necessary condition, let's say we're on a football team. A necessary condition for us to win the game today is that we actually show up. That's necessary. Now, if we show up, does that mean we're going to win? No, it means there's going to be a game, and maybe we win, maybe we lose. But if we don't show up, then we automatically lose. A necessary condition for victory is that we actually show up. Right? You're in the Wimbledon finals. A necessary condition for you to be in the Wimbledon finals is that you actually are in the tournament. See, because if you're not in the tournament, then you definitely are not going to be in the finals. A necessary condition means that if it fails, your conclusion cannot happen. So that's why sometimes it's called the test for divergence. I like to call it the nth term test because that's what I'm looking at. So if I fail either one of these, then my series diverges and I have no work that I have to perform whatsoever. We love it when these fail, by the way. They don't fail very often, but we love it when either one of them fails because then it's really easy. My conclusion is I'm already done. So let's consider, I'll do an example we just did a moment ago. I have the sum from 1 to infinity of 6n squared plus 3 over n plus 1. I'd like to know if this converges or diverges. Well, we don't have any idea if it converges, but I might be able to show it diverges. How? if I take the limit of that, what will I get?
Infinity.
I get infinity. I'm pretty sure I'll write like this, and that's not zero. I needed my limit to be zero. I got a limit of infinity. That means these terms are getting really big, and they're just going to keep getting bigger and bigger and bigger and bigger and bigger. So we can say this diverges by the nth term test. You always give the reason, and we're going to have several reasons. You always give the reason when something diverges, or when we prove convergence, we'll say it converges by this test, it diverges by this test. You cannot converge by the nth term test. You can only diverge by the nth term test. Failing the nth term test guarantees divergence. Passing the nth term test means I now have a problem worth looking at. Okay, so the rule of thumb is you only perform the nth term test if you think it's going to fail. Okay, and that's a fairly simple thing. We could look at that now. It's easy. I know that one. Okay. Now with that, let's look at a very specific series. This is considered one of the most important because it comes up so often. Something called the harmonic series. Now the name harmonic is a little confusing because the term harmonic comes up in math and physics actually quite often. And unfortunately, it seems like every time it comes up, it has a different meaning because it's based on the context of what it comes up with. So the harmonic series has nothing to do with something called harmonic motion, which we study in math and science. Harmonic motion would be, an oscillation like a sine wave. That's called harmonic motion. Harmonic series has nothing to do with that. So I'm not really sure why we use the name harmonic, but I wasn't there when they decided that one. The harmonic series is the following. N equal 1 to infinity, 1 over n. Okay. This is considered one of the most important ones that we study. So what is this? Well, it's going to be 1 plus a half plus a third plus a fourth, forever and ever and ever and ever and ever. Now, those terms are clearly getting smaller, and those terms are clearly approaching zero. That's not even a question. The question is, does this guy here converge or diverge? And we want to just guess.
Converge.
It certainly would seem reasonable. And what I used to do back in the day, when I'm sitting in a lecture or I have a lecture classroom, every single student had a graphing calculator 20 years ago. Now, hardly anybody does. And so what I tell them to do, I go, get out your graphing calculator if you know how to do it. And I want you to add the first, million terms, program your calculator to do the sum from 1 to 1,000,000. And then I just say, wave at me when you have a result. Now, the result might take the whole duration of the class. It wasn't a fast process. And then later in the class, they get back to me and say, okay, I got a result. It's like, 14 point something. It's like, it wasn't very big, which obviously makes us think this is going to converge easily. And boy, would we be wrong. So here's what I want to show you. All right. The harmonic series, if I write out the first few terms, looks like this: 1 plus a half plus a third plus a fourth plus a fifth plus a sixth plus a seventh plus an eighth, and I'm going to put ... Okay. Actually, hold on. Sorry, I'll do one more. 1/9 plus ... plus a 16th plus a 17th plus ... 1 over 32. I'm gonna write down, because I get those eventually. And here's what I'd like you to do. I want to group these guys. Now, if I keep going, I can do this, right? Like Captain America says, we can do this all day. So I'm going to have 1 over 33 plus all the way up to 1 over 64. And then I'm going to have 1 over 65 all the way up to 1 over 128. You notice I'm doing 2 to a power. And we keep going forever and ever and ever. Well, interesting thing. You agree a third is a little bit bigger than a fourth. Agreed? So a third plus a fourth is a little bit bigger than a fourth plus a fourth. Meaning this quantity right here is a little bit bigger than a half. A fifth, a sixth, and a seventh are all a little bit bigger than an eighth. So this quantity right here is a little bit bigger than 4/8, which means this quantity is a little bit bigger than a half. I have a 9th, 10th, 11th, 12th, 13th, 14th, 15th, and 16th. All of these numbers are a little bit bigger than a 16th, and there's 8 of them. So that sum's a little bit bigger than a half. I think you see where this is going. Tell me about this next group. It's a little bit bigger than a half. How about this group here? A little bigger than a half, a little bigger than a half. Now, how many groupings am I going to get if I go to infinity? How many groupings?
Infinite groups.
Infinitely many. And tell me about the sum. If each small group is a little bigger than a half and I'm doing this infinitely many times,
Just infinity, yeah.
be infinity. Oh my goosh. That's why I said this one's so important. But the terms are getting smaller and they're approaching 0. It's going to pass the nth term test. And I just said, passing the nth term test doesn't mean you're going to converge. Failing the nth term test means you're going to diverge. Showing up to the game doesn't mean you're going to win, but not showing up means you're going to forfeit and lose. Coming to class doesn't mean you're going to get an A, but not coming to class means you're going to fail. Right? Oh, okay. It's a necessary condition, but it's not what's called a sufficient condition. So the harmonic series diverges to infinity. That is absolutely huge because we use that one a lot. And this
Is that
kind of a clever proof.
is that the only example of a harmonic series?
That's the definition of the harmonic series.
Okay.
That guy right there. Yeah, it's not a, I don't need an example. That's the harmonic series. Now, I said the harmonic series. We have things that we call harmonic because they act harmonic. Now, this is not meant to confuse, but I want to show I can mess around with things in general. Now, let me show you something here. I've got n equal 1 to infinity of something. What if I said, let's take the first, I don't know, 100 terms. Do you agree with this statement? Is this true or false?
I mean,
Yeah.
works. It's just you split it up a bit.
So I said go up to 100 and then here pick up from 101 and keep going. So are these the same? Do you agree?
Yes.
So let me just be more generic. Let's just call it for some number down the road, we'll just call it C, and then we'll call this one C plus 1. C is just some positive integer down the road. It doesn't matter what it is. What matters is it's finite. Here's an absolute mathematical statement. If you take a finite sum of finite terms, then this term here is finite. Doesn't matter what AN is, that's finite, okay?
Can you repeat that, Professor?
Say again?
Could you repeat what you just said?
A finite number of finite terms when added is finite.
Oh, okay. Okay.
Matter-
Thank you.
It doesn't matter how big, but what if they're really, really big? Then I get a really big finite number.
Right.
So see this guy here, if this guy diverges, it's not going to be because of that. It's going to be because what happens the rest of the way. If this guy converges, it's not going to be that. It's going to be what happens the rest of the way. So here's kind of a weird, quirky thing. You're adding an infinite number of terms. If you decide to remove, let's say C is 1,000, let's say C is 1,000,000, let's say C is huge. I decide to remove that many terms. I am now subtracting a finite number from my total. If my total were infinite to begin with and I subtract a finite number, won't it still be infinite?
Yep.
And if I had a finite total to begin with and I subtract a finite total, then obviously it's finite. So this guy and this guy have the same, what we call behavior. They won't be the same numerical value, but they either both converge or they both diverge. Because subtracting a finite quantity isn't going to affect convergence or divergence. Now, at first that's like, whoa, but if I said, now let's subtract the first few terms, is that going to affect the fact that this is infinite? If I said, let's take out the first few terms. let's use the harmonic very specifically. What if I asked you to do n equal 4 to infinity of 1 over n? What did I just do? I just removed the first 3 terms. Do you agree? Can you say there? Is this a true statement mathematically?
Yes.
N equal 1, n equal 2, n equal 3?
Checks out.
This is everything. This is starting at 4, so I don't have 1, 2, or 3, and those are the first 3 terms. So that quantity right there, that's 1 and a sixth, so that's 11 over 6. Okay. If this is infinite, and I just subtracted 11 sixths, wouldn't this still be infinite?
Yeah.
That's my point. It doesn't matter how far down the road I start, because that was infinite to begin with. Now, here's a statement that sometimes is confusing. This is the with a capital T. This is the harmonic series. This is A with a little a harmonic series. Oh my goodness. Anything that has this as its argument and you're going to infinity is called a harmonic series. The harmonic series is the one that starts at 1. And the reason that's important is if I know the behavior of that guy, then I know the behavior of this guy. I don't have to prove it. This is a harmonic series. In fact, I lopped off the first 3 terms. So you say, is it smaller? Well, they're both infinite. So let me ask you a question then. I'd like to know the behavior of the following. What do you think? Converge or diverge, and why? I've already shown you the why. Now you got to tell me.
Can't you
Diverge.
pull out a 4 from the sum?
I like that.
I mean, it already looks like similar to the harmonic series, so it's a harmonic series. So
Well, it is 4. How about, I like what you said before. How about it's 4 times the harmonic series?
4 times infinity. Okay.
So this, we'd say, diverges. But why does it diverge? Because that's a harmonic series. It's a divergent harmonic series. The 4 had nothing to do with convergence or divergence. It was there to distract you. Okay. And I like what you said. I factored out the 4. Oh, makes perfect sense, right? Similar question now. Converge or diverge? New problem. It's not equal to this anymore.
Diverge.
It diverges because it's still the harmonic series where I've lopped off 9,999 terms. So you can still say this is a harmonic series. You don't have to prove it. I just proved it for you a moment ago. So sometimes it's a piece of cake to identify something that diverges because it looks like something you already know diverges. And that concept is huge in this class. If I prove something and then I take something that acts the same way or looks a lot like it, it's almost certainly going to have the same conclusion. Now, when something converges, figuring out what it absolutely adds up to, that's a different issue. Our goal is not to figure out what it adds up to. Our goal is to figure out if it converges or diverges. In reality, I can always use a computer program to figure out what it adds up to. Okay, I'll explain that one later. How do you add up an infinite number of terms on a computer? You can't add up an infinite number of terms on a computer, but if it's converging, that means your terms are getting really small, really fast. So maybe you don't have to add up that many to get a good feel. That's kind of what happens here. Now we're going to look at a couple of very, very specific types of series. The first one is called a telescoping series. Okay, it's the form. Now, again, a lot of these notes are online and you can go back through them and hopefully it makes perfect sense. But a telescoping series is a series where things cancel. They kind of cancel each other as you go. So for example, what if I had a sum, let's say n equals 1. Actually, I'm going to use I in this case because I'm going to use n for something else. Let's say I equals 1 to infinity of 1 over n minus 1 over n plus 1. Now, this is confusing right off the bat. Now, let me ask you a question. Is the following statement true? Is the following statement true? Oops, sorry. I should probably put something in there. There we go. Is this true? Oh, you know what? I'm just messing up all over the place. These got to be
Yeah,
odd.
I was gonna say, how do you have I
Ah,
going to infinity
just-
with
no.
ends?
This is the point in the day when my coffee is no longer useful. Sorry about that. Okay. Is that a true statement mathematically? Now remember how I
Yes.
started the class? Yes or no?
Yes.
Yes. This is the harmonic series. This is the exact same series with one term removed, but they're infinite. Oh my goodness. It's an infinity minus infinity, in other words. That's not useful. It's true, but it's not useful at this point. This is called a telescoping series, and I'm going to show you what's actually happening. This is true, and I can do this, but I don't know how to, that's infinity. I have an infinity minus infinity form. So here's what we're going to do instead. We're going to write out the first n terms. Okay. Now, this is an infinite sum. It does not equal the first 3 terms or the first 12 terms or the first 27 terms. It equals the infinite number. So I want to just write down the first n terms. Remember I said this is called S. So I want Sn. That's why I was saving the n. Okay, well, what does that mean? Well, okay.
Is that a capital S or a small s?
Usually capital S, S for sum,
All right.
Yeah, a big S. Or as my kids like to say, a big ass is, big S, I don't know. All right. So if I replace I with 1, then what's my first term? 1 over 1 minus 1 over 2. Okay. Now replace with 2. All right, 1 over 2 minus 1 over 3. All right, well, this is pretty exciting. And I'm going to do this for a while. And eventually, let me do the n minus 1 would be 1 over n minus 1, oops, minus 1 over n. And then the nth term is when I replace this with n. Okay, everybody see that? I've just added up, that's what the plus dot, dot, dot. I just added up the first n terms. How do I know? Because if I replace that with n, that's my nth term. This is the one right before it. All right. This is not the answer to the question. This is how I'm going to figure out the answer to the question. Okay. You guys notice anything interesting? Like if I removed all the parentheses, what do you notice?
A lot
Everything
of them
cancels
cancel out.
after 1.
On and on and on. Bloom, 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 bloom. Does every single term cancel? Not
Yep.
every.
Except the 1 over n plus 1.
Do you agree that those would be the only 2 left? Does everyone see that those are the only terms that
Yep.
cancel? That's why we like telescoping series. So the sum of the first n terms is 1 minus 1 over n plus 1, which I can't see there. I did it by figuring it out. Now, how does this help me? Well, here's a major, major, major statement that is always true. I'll put it up here. S, which is the infinite sum. S is the sum of from 1 to infinity. S is equal to the limit as n goes to infinity of Sn. Doesn't matter what your series is. This is absolutely always true. Remember what this meant? This meant the sum of the first n terms. So if I allow n to approach infinity, then I would get all the terms. That makes sense, doesn't it? So Sn means I added up a finite number of terms. It's called the nth partial sum. I added up that many terms. We just added up the first n terms of this series and we got this value. What if n is really big? What if n is bigger and bigger? In fact, what if n grows without bound? Well, that's where the infinite sum would come in. So for this problem here, I was looking for S, I calculated Sn. So can we say this? Yeah, that's the whole point. And what is this limit?
Just one.
Just one. Cool. This limit is just one. The telescoping series is special. It's special because you get the cancellation. You don't get that in general. You get that on this one. There's only a couple of series, this being one of them, where I can actually calculate the infinite sum. I can directly calculate and say this infinite sum is going to add up to this number. The vast majority of time, all you can do is tell me the series converges. Again, we would need technology to figure out what it converges to, or at least give a reasonable approximation. But the telescoping series, you can say, no, this infinite sum is equal to 1. Whoa, that's kind of cool. Okay, so telescoping means you're going to get the canceling effect. And the way you do it, I did not put an equal sign between here and here. No, this is only n terms. N might be 5, n might be 1,000. This is infinite. I figured out what the nth sum is, and then I took its limit. And that's my infinite answer. In no situation does the infinite sum equal the partial. That makes no sense. Unless I have a series where every term is, I'm going to guess, 0. And there's no such series where every term is 0. That's not actually a definition. The definition of a series is your first term cannot be 0. In fact, in a series, you can't actually have any terms of 0. So if the only way these could be equal is every term is 0, then they can never be equal because no series can have zeros. Whoa. Yeah, can't get zeros in a series. It can't happen. Oh, well. All right. Now, the next one is considered one of the more important ones. And this is one you hopefully did actually in baby algebra. And that is the geometric. Oh, okay. So we did geometric last time. Okay. Now, I'm going to show you something that you may or may not have seen in an algebra class. And I really wish you had seen it. Okay. Now, I'm going to tell you a story. It's a legend. And what you have to understand about legends don't have to be true to be important, right? When you hear a legend about something, it's usually overblown. You know, somebody was a hero, they did great things.
This is about Chuck Norris.
No, Chuck isn't involved in this one. This one predates Chuck by a little bit. Okay. There are great stories that people tell that over time build up. And I know a lot of them, a lot of martial arts history is based on legends, and storytelling. It's awesome. Well, this is one of my favorites. My favorite mathematician probably is Carl Friedrich Gauss, because he's basically the founder of everything involving linear algebra. I mean, if you've ever done matrix algebra, they call it Gaussian elimination after this guy. But apparently, as the story goes, he was an obnoxious little kid. Okay, now he grew up in the environment where everybody went to school at the same time. In other words, you had the one-room schoolhouse, maybe, K through 12, all in the same place. Yeah, I mean, there was a time when that kind of stuff went on. And so, by the way, you didn't take notes with pencils and paper. Okay, it was a couple hundred years ago. Why didn't you take notes with pencils and paper then?
Stone and chisel, or
Well, first of all, it didn't exist. No, the only paper that existed basically was newspapers, and that came later. And no. So what you did was you had your little easel, like think of it as a chalkboard, and you had your piece of slate or granite, like big piece of chalk, and that's what you wrote on it, and you turned things in. So one day, as the story goes, see, whether it's true or not, it's irrelevant. As the story goes, little Carl Friedrich was being particularly obnoxious this day. So the teacher says to him, all right, Carl Friedrich, I want you to add up the first, million positive integers. In other words, what's 1 + 2 + 3 + 4 up to 1,000,000? Figuring it would keep the kid busy for a while, because the kid was, off the charts genius. So of course, a few minutes later, he comes back with an answer, which didn't really help the situation because he got the answer a little bit too fast. So of course, you say he just went to the internet, right? Yeah.
Oh, way. He used symbol
A computer back then was a sandbox with a stick where you could, write your problems out. That was a computer back in the day. So here's the question he was asked: 1 plus 2 plus 3 plus, plus 99999 plus a million. Okay, he's asked to do this. So being like any good mathematician, very lazy.
That's only 100,000.
I lost it. Thank you. I need one more zero. All right. So like any good mathematician, he was lazy. He says, how can I do this easily? So he says, what if I do this? What if I just simply write all the numbers in reverse order? What a crazy notion. What does that add up to, by the way? Isn't that 1,000,001? Huh. What does that add up to? Oh, also 1,000,001. In fact, what does every one of these totals add up to? Would you agree that every one of these adds up to 1,000,001?
Yep, yep.
So did he add 1,000,000 numbers up? Nah, he outsmarted the question. He's got 1,000,000 million and ones. Is that the answer?
No, you have to multiply them, right?
You have to divide them by 2 because you have a double series.
Because you counted it twice. And that's the answer. Now, what kind of a series is this? I'm adding 1 to each term. You remember we defined the sequence yesterday.
Arithmetic.
Arithmetic. Yeah, I don't know why it's spelled arithmetic, but we say arithmetic. I don't know. It just sounds really cool. It's like, adult and adult. I often say adult, if I'm in the right crowd, because it just sounds cooler. It's an arithmetic, I'm having fun, an arithmetic series. And the formula for an arithmetic series is actually, believe it or not, n over 2 times a1 plus an. In other words, add up the first term and the last term and multiply by n over 2. Why the first and the last? Because the first and the last is what everything's going to add up to no matter what. We were incrementing by 1, but what if we counted by 5s? Well, then we'd also count backwards by 5s. It would still be the same thing. So little Carl Friedrich figured out a brilliant formula. That's not the one we're going to do, but it's the logic behind it that we're going to do. He said, I'm going to add an absurdly long list of numbers, but I'm going to be more clever. I'm not going to physically add them. That would take too long. So he figured this out. So now we want to do something similar with a geometric series, because this is one of the more important results that we're going to see. So remember what geometric means. Geometric means I'm multiplying by the same value, or consecutive terms have the same ratio. It's the same thing. So in a geometric series, I have A1, and then A2 is A1 times R. And then A3 was A1 times R squared. And then eventually the nth term is A1 times R to the n minus 1. You guys told me this yesterday. Do you remember that? So these are the terms of a geometric sequence. I use like 2, 6, 18. I went like that. Here's what I want to do. I want to add these up. I would like to add up A1 plus A2 all the way up to AN. I want to add up the finite number of terms. I can't add an infinite sum until I first figure out what the finite sum is. Oh, and then I can take a limit. That makes things a lot easier. I would like to add these guys together. Everybody see that? So I'm just going to add these. So clearly this is going to be A1 plus A1R plus A1R squared plus, and then this one A1R to the n minus 1. Great. Can I do the same thing I did before and put these in reverse order? Would that work?
No, but you could factor out an A.
Yeah, but I want to do something clever. Let me ask you, if I did this, A1R to the n minus 1, then this would be A1R to the n minus 2, all the way down to, and this would be A1. If I add these, will I get the same sum? No, I'll never see the same sum twice. That only worked because I was adding by the same amount before. Now I'm multiplying. That's not going to work, but there is something that will work. Okay. I don't need this anymore. Tell me, what is negative R times Sn? If this is the sum of the first n terms, then what's negative R times Sn? Well, wouldn't that be negative A1R minus A1R squared minus A1R cubed? The second to last term would now be minus A1R to the n minus 1, and then that one would be minus A1R to the n. I just multiplied every one of these by negative R, so my exponents all increased by 1. Okay. Why would I want to do such a crazy thing?
So you can factor out the R.
Not factor out.
Because
but
now you can minus
if not minus, add.
add. Yeah.
What happens
that's
when I
right.
add them?
Yeah. You
You see it?
take them out.
Does everybody see it? If I add them, every single thing is going to cancel except that one and that one. Now, again, whoever figured this out, this was genius. I take no credit for this. This is brilliant, but it's the same sort of logic that we just did with the arithmetic series. If I multiply every one of these guys by negative R, I create a new series where every term cancels except those guys. So let's add these together. I have Sn plus this. So right now I have Sn minus R times Sn. And what am I getting? Only this. Now, someone said factoring out. Now is when I would want to factor out the A1. I didn't need to before, but now I will factor it out. Now, what about on the left side? Can I factor out the Sn? So what does Sn equal? It equals this over 1 minus R. Some of you may have seen this formula before. This is the nth partial sum, or the sum of the first n terms of a geometric series. It's not the infinite sum, but that's easy enough to find in a moment. This is genius, because what if n is huge? All I need to know is what's the first term and what's the R, and this is what we'll get. That's so cool. Let's do an example just to convince ourselves that this actually is true, by the way. That's always a good idea, because if I wrote something down incorrectly, I may not see it. So I'm going to use one we did last day. Last day we did 2, 6, 18, 54. Let's stop here. So that's my A1, A2, A3, A4, A5, A6, and I want to add these together. So first thing I'm going to do is I'm going to get out my calculator and actually add them together. That's why I didn't do too many. All right, I just got 728. All right. I'm doing a quick check to make sure that I'm doing this correctly. Now, I already know I am, but I'm showing you how you can check it. So let's use this formula. So in this situation, my A1 is clearly a 2. What's my R?
3,
3. And what's my N?
6,
6. Okay, so for this problem here, my S6 is 2 times 1 minus 3 to the 6th power over 1 minus 3. Okay, so I do this on my calculator. That'll be 2 times 1 minus 729 over negative 2, which is 728. Nah, crowd doesn't go wild. We're expecting to get the right answer. I always like to do a quick error check. Now, here's the thing. I want to take the limit as n goes to infinity. Easier said than done. How do you take a limit of r to the nth power? That's not trivial. So that's the next thing we're going to do, because that result is absolutely huge. This is the nth partial sum. But do you all agree that as this grows, that this sum is going to be infinite if I keep going forever? Is that pretty obvious that that's going to be infinite? I mean, each term is bigger than the one before, and they're getting bigger and bigger. Yeah, so I'd like to know, when is it going to converge? Can anybody give me an example of something they think might converge? A geometric?
fractions.
Maybe if my R was fractional. That really is the key. So you hit it on the nose. So we want to figure out R to the n. Now, here's where I want you to pull out your calculator for a moment. Because I want you to see evidence of what I'm telling you. We're going to put large numbers in our calculator and see what happens just to get an idea. So here's what I'd like to do. My next goal is to find the limit as n goes to infinity of R to the nth power. Now, there's a lot of possibilities. For example, what if R is 0? Well, that's easy. What if R is 1? Well, that's easy. What if R is huge? Okay, what if R is small? What if R is negative? There's a lot of possibilities. Okay, so let's do the easy ones. Okay, I have R is less than -1. I have R equals -1. I have -1 is less than R is less than 1. I have R equals 1. I have R is greater than 1. This is actually the easiest breakdown of all. Okay, now I'm going to do the easy one. What if R is 1? Then what's that limit?
Didn't we say that you can't actually do 1 to infinity, like 1 to infinity does not equal 1? Isn't
No,
that
one-
something you?
1 to the infinity would be 1.
Oh, okay.
If my base is exact, not approaching 1. Now, see, don't confuse it with the limit of E. I'm not approaching 1. I'm saying, no, R is 1.
Got it.
What if R equals 0? Then wouldn't we agree that it's 0?
1.
Now, if R is bigger than 1, R is 2, R is 5, R is 1,000, and I'm raising it to a power and its power is growing, I think that
It's
one's,
infinity.
that one's easy. Now let's go this way. R is -1. If I raise -1, and by the way, n has to be integer. N can't be decimal value. So first of all, these n's have to be integers. So when I'm going to infinity, it's 1, 2, 3, 4, 5. If I take -1 and I raise it to a power, doesn't it just go from -1 to +1 to -1 to +1 forever, never, never? Does that make sense? So what's the limit as n goes to infinity of -1 to a power?
Not exist.
Yeah, that's kind of like the sine wave or the cosine wave. I'm just bouncing forever. That's a DNE. Ooh. Now, the most evil thing involved is this guy. I have a large negative number raised to a higher and higher power. So not only are my numbers getting bigger, they're also oscillating. Here's the way it actually looks. This is what's happening. It's ballooning out of control. My next number is bigger and positive. My next number is even bigger but negative. My next number is even bigger but positive. Are they approaching even positive or negative? No.
So another does not exist.
Another DNE. So guess what? We don't like those guys. But we're not really crazy about that guy either. Oh, no, that kind of, I think this is the guy we want to talk about right here. That's the only one that matters. So here's what I'd like to do. If I take a small fraction and I raise it to a larger and larger power, this is kind of a no-brainer. If I said, I want you to take the limit as n goes to infinity of 1/2 to the n, wouldn't that be the same as saying, I want you to take the limit as n goes to infinity of 1/2 to the n? Isn't that the same thing?
Yep.
And as n grows without bound, that guy's getting infinitely large really fast. And so this is a transient term, and that's kind of a no-brainer. Do you agree? That
Isn't
was
there-
easy. But here's
Isn't there
the-
something that relates that to like the p is greater than 1 or Greater than or
not
equal to 1.
exactly. Hold that thought, because that's actually a major deal tomorrow. Hold that thought.
Okay.
It's a little bit different because now we're talking about that's a situation where you had a number raised to successively larger powers. Here's a case. I'm sorry. The
is
base-
1 over
the
x
base
to the
was
p.
changing. Here's the exponent is changing. So that was more like polynomial. This is more exponential. Now, here's what I'd like you to do. Take, 999 or 0.999. That's really close to 1. Now, I want you to raise this to a large power on your calculator. Okay, well, I'm going to raise it to the millionth power. A million is not infinity. Okay, a million is big, but it's nowhere near infinity. So I need one more zero. Okay, so I am raising
0.
999, and my calculator says, okay, I'm sorry, but that doesn't make any sense. I have a number that's very close to 1. Think of it this way. If this is exponential decay, then I'm losing 0.1% maybe every year. So I have 99.9% next year that I have this year, and then I have 99.9% of that. I'm always going to have almost the same every year. Now I'm going to do this for 1,000,000 years. My calculator said 0. Why the heck would my calculator say zero? This can't be zero. What does it mean? It means the number was smaller than 10 to the negative 99th power, because that's as far as my calculator could go. Oh, let me back off a little bit. Let me do 999 to the 1000th power. Okay. Oh, when I did that, I got something on my screen. But if I kept going and kept going and kept going, that number is so small that my calculator couldn't even measure it. By the way, I put in the millionth power. That's not infinity. So this is an absolute. If you take any value between -1 and 1, including a negative number, and you raise it to a larger and larger and larger power, what's happening to the size of the number? It's approaching 0. So this limit is 0. Remember, we're doing the limit as n goes to infinity. So that's sort of the key component. So I want to talk about geometric series, but I am only interested in geometric series that converge. I'm not interested in these guys. I'm not interested in these guys. I'm interested in these guys. So
Professor, I have a question about
Yeah.
this as well.
Yeah.
We were talking about this, the negative fractions. So it wouldn't be like -1/2, and then it'd be like -1/2 squared, so that'd be positive. So it would
right,
add.
the negative is still going to make oscillate, but the 1/2 is approaching 0 rapidly. So think
Got it.
squeeze theorem. Think squeeze theorem again, like we did with the sine. Okay, so although it's bouncing, it's going like this. In other words, it's bouncing and getting closer and closer to 0. Yes, it's alternating sign, but it's still getting closer to 0. So the
Got it.
ultimate limit. And by the way, that's a very important question, because it does seem to kind of defy reason at times. So here's the question now. N equals, so I'm going to do n equal 1 to infinity, a1 r to the n minus 1, because this is sort of our generic form. Everybody okay with that? This is a geometric series. So quick check, this would be a1 r to the 0 plus a1r plus a1r squared forever and ever and ever and ever. All right. I am only interested when this answer is finite. I am only interested in this answer if it converges. And it will only converge in this case. And so the way we generically, universally state that, to say r is between -1 and 1 is equivalent to saying the absolute value of r is what? Anybody want to try that?
Less than 1.
Strictly less than 1. So this is sort of the universal way. These say the exact same thing. This is just a little more convenient, because now it doesn't matter what the sign is, only the size. I need r to be smaller than 1 in size, regardless whether it's positive or negative. So if I have a geometric series where this is true, then I can actually finish the problem. So now that we understand the limit and we only are considering that very, very narrow band of numbers, now let's go back to my nth partial sum. We said the nth partial sum of a geometric series was a1, 1 minus r to the n over 1 minus r. If the absolute value of r is less than 1, then s equals the limit as n goes to infinity of Sn. Agreed? This is always true, but if this is less than 1, then what must this equal? What's happening to this term if the absolute value of r is less than 1?
Close to 0.
It's approaching 0, and its limit is 0. So what does that leave me with? Simply a1 over 1 minus r. Oh, that is so cool. This infinite sum is equal to this. Now, if I factor the a1 completely out, right, it's the same a1. So it's really that's all I get if this is true. Whoa. So let's do a simple example of this. And we've all seen this problem before. All right. Tom is very bored, so he decides he's going to go on a walkabout, but he's in his apartment. And he's very, very focused and very linear minded. So what he's going to do is every 5 seconds, he's going to start at one end of his apartment, and every 5 seconds, he's going to walk halfway across his apartment. 5 seconds later, he's going to walk half of that. 5 seconds later, he's going to walk half of that. And then 5 seconds, and so on and so on. He's going to do this. So he half of, and then he did a fourth, and then he did an eighth, and so on. First of all, how long will it take Tom to reach the other side of the room? Anybody?
He'll die before reaching it.
No, that's, you don't know about Tom. He's got special gifts. All right, how long will it take Tom to reach the other side?
Forever.
Infinite.
Forever, okay. Funny thing about calculus, we have forever. We have an infinite amount of time. So if I said, add up these numbers forever, shouldn't basically you reach the other side of the room? So here's what I'm asking you to do. This is a crazy statement. I am asking you to add up a half plus a fourth plus an eighth plus forever and ever and ever. Isn't that a geometric series? In fact, it's a geometric series. What is the only thing I need to know in a geometric series? What is the first term? What is the constant ratio? Well, in this case, my first term is a half. What is my constant ratio?
1/2.
It's also a half, okay. So can I say this is equal? Can I actually calculate this? Well,
1.
the R is smaller than 1. So according to this, it's supposed to be a half, 1 minus a half, which is 1. If I add this up forever, I get 1. Whoa. So in baby algebra, remedial algebra, you guys did geometric series. They weren't series, they were partial sums because you added up the first 5 terms, the first 10 terms. And then they would refer to the infinite series. Well, that's the actual series. But when the R was smaller than 1, you could do the calculation really easy. It's actually much harder to add up the first 10, the first 1,000, the first million terms. It's much easier to add the infinite sum because then I only have to do this. Whoa. So a geometric series will converge if the absolute value of R is less than 1, and it will converge to this 100% of the time.
Will it always be 1?
Well, no, that's just because I chose.
Oh,
those.
okay.
Yeah.
Can I ask you, can you go,
Oh.
can you explain how you figure out the R? Because I don't see it.
Oh, what's the definition of R? It's the ratio of consecutive terms. So an eighth over a fourth or a fourth over a half. Or if you want to go forward, what do I have to multiply to get to the next number? It's the same thing.
Always,
I
what
have,
do- it's always what do I have to multiply to get the next number?
Yeah, that's why if you took the ratio of any two numbers, the second number over the first number is the R.
Oh, okay.
That's it. That's the definition. Question.
I have a, so in the word problem or in the scenario we just posed, where you have a person walking half the distance to the other wall,
Hmm?
what does the 1 mean? Given infinite time, he will reach
So if I
the other
said
side?
halfway, how much of the room did I walk? Half. If I walk another fourth, now I've walked 3/4 of the room. So 1 means I walked the whole room.
But
So
but
think
you're
about it.
saying,
Okay. Very loud airplane, as opposed to those quiet airplanes. If you think about it, say, okay, after 5 seconds, I walk half the room. After 10 seconds, I've walked 3/4 of the room. 15 seconds, I've walked 7/8 of the room. So at any moment I've stopped, I can tell you exactly what fraction of the room I've covered. So when I've covered the whole room, I've walked the whole room. Right? I think, or 100% of the room, if it helps think of it that way. Now let's do a different one. Let's suppose I have, let's say, excuse me. I'll start with something fairly simple. I've got 81 minus 54 plus 36 minus 24, forever and ever and ever. If you think you see a pattern, then that is the pattern. Is this geometric? I'm not going to tell you any information other than this. Have I given you enough information for you to make a conclusion? Well, hopefully you get out your calculator or you do it in your head. What is negative 24 over positive 36? That's negative 2/3. What's 36 over negative 54? That's negative 2/3. What's negative 54 over positive 81? That's negative 2/3. Yeah, this is a geometric series where the R is what? Just said it. What's the R?
Negative 2/3.
Negative 2/3.
Negative 2/3. And what's my first term? 81. Do we have enough information now to determine what this sum will add up to? By the way, at some point, am I gonna get really small fractions and they're getting smaller and smaller and smaller and smaller? Sure. Yeah, I just keep multiplying. I have 2/3 as much. Eventually, I'm gonna have something really small and eventually it's gonna kind of go away. So this adds up to, this is equal to 81 over 1 minus -2/3. Now be careful because the R is negative. So this would be 81 over what, 5/3? So that'd be 243/5. Okay. And that's my answer. Well, if I did like 81 minus 54, well, that's 27. And now I'm gonna add this, now I'm up to 63. Now I subtract this, now I'm down to 39, right? I'm gonna eventually hone in on something that looks like that. But this was much easier than trying to add pieces. So a geometric series, I have to first identify it's geometric, but then I can use the fact that if the absolute value of R is less than 1. All right, let's try another one. All right, I have, let's say, sorry. Trying not to sneeze here. Let's say I have 12 minus 18 plus 27 minus 81 halves plus forever, never, never, never. Okay.
It's growing, so you have a positive rate, or you have a rate larger than 1.
I don't know if you guys can even hear me when those planes are going by, but man, they're loud. Is this geometric? Do I have the same ratio? This over this, this over this, this over this? Yes, I do. So what is my R and what's my A1? Okay, I got
Three-
-3 over 2.
3 over 2?
-3 over 2.
Negative 3 over 2. Okay. So is this correct?
Not at all.
No,
Why not?
because
It's
your
greater than
rate
1.
is greater than the absolute
Yeah.
value of 1.
So my absolute value of R is greater than 1. Therefore,
Goes to
Infinity.
infinity.
this actually not infinity, worse. This is the worst. This is the, I'm bouncing around. This diverges without limit. If you just said it diverges, you're okay. But by the way, it does not diverge to infinity. Why?
Because it's negative.
Well, no, it's not that, because I started positive, and then when I added -18, my total is now negative. Do you agree? Then when I add 27, now I have a bigger total, but it's positive. Now when I add this, I have a bigger negative. The next one's gonna be a bigger positive. So I am bouncing, and each time my number is gonna be bigger than the previous number, but it's gonna alternate signs. So I'm neither approaching positive infinity nor negative infinity. I'm bouncing into, right? Like I said before, it's like this.
So yeah, R is less than -1.
That's the ugliest of all types of divergence. So if you just said it diverges, say it's a geometric series where the absolute value of R is greater than 1, therefore it diverges. That's all I gotta say. You don't have to say without limit, but it is without limit in this case. Crazy. Now I got one of my favorite problems to deal with, okay, is decimals. Now, the definition of a rational number. The definition of a rational number is any number that can be written as a quotient of integers. That's why integers are rational, because the number 4, I could write as 4 over 1, I could write it as 8 over 2, I could write it as 12 over 3. All of those would be correct representations of 4. Agreed? So integers are also rational numbers. Now that's the definition of a rational. But what's the definition of an irrational? This is where we get in a little bit of trouble. So there's an alternate definition of rational numbers that involve decimals. And that's the one we're going to actually consider. So a rational number, okay, I have a half, okay, piece of cake. But if I have a third, I don't write 0.3. I could do this until my arm gets tired. I could do that, but we have a more.
Or just write a bar,
Or a 3 bar.
What does the bar mean?
repeat
Repeats
It repeats how many times?
indefinitely.
Forever. Oh, okay, so now we have the alternate definition of a rational number. Any number with a terminating decimal sequence, and by the way, there's nothing in your life that is easier than converting a terminating decimal sequence back into a fraction. Really? Yeah, let's suppose I give you the number 2.3716, and I want you to write that as a fraction. Oh my God, what am I going to? Oh, that's it. Writing a terminating decimal as a fraction, it's really the easiest thing you'll ever do. You know, that's not the question. It's this guy. Can I go from a decimal? Now, if this is the definition of a rational number is any number with a terminating decimal or an infinite repeating pattern. Now that's the key, repeating pattern. By the way, is the repeating pattern always just one number continued? Could it
Not
be
always.
2 numbers or 3 numbers or 25 numbers? Yeah, doesn't matter how many numbers, but that pattern is repeated forever. So the definition of an irrational number, pi root 2 e, it's an infinite decimal that does not repeat. Oh, okay. So there's 3 possibilities. First of all, it's finite or terminating, infinite, but infinite has 2 possibilities, repeating pattern or non-repeating pattern. The definition of irrational is the non-repeating pattern. Repeating pattern is rational. Anybody here with a calculator in their hand can easily take any fraction, stick it in their calculator, and tell me a decimal equivalent, and even tell me the repeating pattern if they can see it. What if you started with the decimal? Can you work backwards and tell me the fraction?
There's
Not
a
if it's
button in the
rounded.
calculator for that, actually.
Actually, there is no technology that exists. You cannot take an infinite decimal sequence, take a rounded off decimal, and then convert it to where it came from. That's an absolute impossibility because there are an infinite number of correct results, and only one of them would be the one you want. You can't take a round off number and work backwards. That's impossible. Yeah, it doesn't matter. A million years from now, still, if I say I'm thinking of a number and it rounds to 0.5, what number am I thinking of? Well, there's an infinite number of things that would round to 0.5. But what if I said I'm thinking of a decimal? And I'm thinking of the following. I'm thinking of, let's say, 0.45 with the bar. I'm going to start something really simple. I'd like to know what fraction that came. Now, the fact that I put the bar means that I know it's going to repeat forever. So do you agree that there is a fraction that should equal that? Does that seem reasonable?
Yes.
Yeah. So how the heck do we find it? Well, because this is a geometric series. It is? Yeah. I'll prove it. Oh, see what I'm doing? I'm moving the 45 2 decimals at a time, forever and ever and ever. So is this geometric in nature? Absolutely. This is exactly geometric. All I need to do is identify my first term and my constant ratio. All right. I'll do the first term. There. Okay. Can anybody tell me the constant ratio?
1/100.
1/100. Good, because I'm moving 2 decimals at a time. Now, because I'm going to be putting a decimal in my numerator, it may be prudent to just go ahead and write it like that. Why? Because these are exact values. I'm not rounding off to get these, but it might be easier to manipulate. If you put 1/100, same thing. But I don't really want a fraction where my numerator is a decimal and my denominator is a fraction. That'd be kind of goofy. So I'm going to go out on a limb and say, I'm going to put an equal sign right now. All right. What would my denominator now be?
0.99.
0.99. Can I? 45 hundredths over 99 hundredths. Can I reduce that to, can I legally just write 45 over 99? Is that legal?
Yes.
Does that reduce further? I can pull out a 9, so that would be 5 over 11. Huh. Well, that's interesting. I wonder what would happen if I put 5 divided by 11 into my calculator. Oh, 4, 5, 4, 5, 4, 5, 5, 5. Does this always work? Yes. Absolutely always works. If you have the repeating pattern, absolutely, you can work backwards and figure out the fraction it came from. Pretty cool, huh? Now, some of you may have done this in a remedial algebra class for something simple like a third. Now I'm gonna blow your mind on this one, and you can make some money at a party and you bet people and things like that. People, I don't do that kind of stuff, but you might. All right, I'm going to put 3 numbers down. Excuse me. This is all right. Let's start with, how about if I did 0.9 with a bar, and I'm going to claim that this is equal to 1. Now, this is what I'm saying. You can make some money at a party. You walk up to someone and say, hey, I have 0.9999, you know, I have 0.9s and it's equal to 1. And of course, somebody would look at you like you're crazy and say, I bet you it's true. This is where you reel them in, you know, the whole thing. Of course, that's completely absurd. Do you agree? 1 equals 0.9. I'm going to show you 3 different ways why this is true. All right. First of all, what's 1 minus 0.9? Well, let me write a couple things down. I just want to see a quick pattern here. If I do 1 minus 0.9, it's 0.1. This would be 0.01. This would be 0.001. Okay, I get the point. Well, no, the point is, when does the first 1 show up? Oh, so when I had 1 9 after the decimal, it showed up in the next spot. When I had 2 9s, it showed up in the second. When I had 3 9s, it showed up in the third. When I have 4 9s, it shows up in the fourth. Okay. How many 9s do I have here?
Infinite.
So when does the first 1 show up?
Never shows.
Never
up.
shows up. Proof number 1. That is a mathematical proof. If this minus this equals 0, then they have to be equal. Whoa. You like that one? Second one, let's do the geometric series that we just did. So if I said 0.999 forever and ever and ever, or actually, let me do it with the 0.9 again. Then this is 0.9 plus 0.09 plus 0.009 plus forever and ever and ever. So my first term is 0.9. What's my constant ratio?
1/10.
1/10 or 0.1. So 0.9 adds up to 0.9 over 1 minus 0.1, which is 0.9 over 0.9, which is, that was proof number 2. Proof number 3 is the easiest one of all. So if you forget proofs number 1 and 2. All right. What is 1/3? Isn't that 0.3 with a bar? What's 3 times 1/3? Well, that's 3 times 0.3 with a bar. What do I have on the left?
1.
What do I have on the right? It's crazy cool. I
All
could
right.
make some money over the weekend. Hey, buddy, I bet you 0.9 infinite repeating decimals equal to 1. Now round off, exactly identically equal mathematically. Whoa. Yeah, I just showed you 3 different ways. This is powerful. This one is more powerful than the difference being a bunch of zeros. That's a little bit more abstract. This one here is like, no, that almost feels like you're cheating, you know, but that's the most absolute of all. So a geometric series, as long as the absolute value of r is less than 1, that geometric series is going to converge, and it's very simple to calculate the convergence. That's why I said it's a really important one, because it comes up in a lot of situations. Now, that's what I wanted to get covered today. So we had a lot of stuff today, none of it terribly complicated, just a lot of stuff. So do be checking the notes that I posted on Canvas. You'll know, because you'll see series, you're going to see harmonic series. Which I can't remember which. I think I have geometric, I think I have telescoping. Okay, there are some things that we haven't got to yet that I posted. Well, that's obviously tomorrow and Friday's lectures. So proving things converge or diverge, that's sort of the next thing. And that will start tomorrow. All right. So it's a good stopping point.